In this section, I want to highlight differences between what we're going to call uniform circular motion and non-uniform circular motion. And so in each case, we're going to focus on the components of the acceleration and how we're going to define each of those in each scenario. So we're going to start with uniform circular motion, and uniform circular motion is motion in a circle where we have the constant speed. I do want to emphasize, so constant speed is not the same as constant velocity, right? So we have constant speed, but we do not have constant v. And so looking at this just diagram here on the right, we have an object moving in a circle. Those green vectors, those are velocity vectors. And so you can see at each point in this case, we know that we have constant speed because the magnitude of those green vectors is the same at each point around the circle. So that's why we can say we have constant speed. But you should also notice that those velocity vectors are all pointed in different directions, right? So if we're moving around in a circle, our direction is continually changing, so we cannot have constant velocity because velocity has magnitude, which is speed, and direction. We've got to take into account both pieces. So when we're doing uniform circular motion, if I have constant speed, then we know that each point along the circular path, the acceleration vector has to be perpendicular to my velocity vector, right? And again, that's shown here in the picture. So we have this acceleration is the orange piece that's directed perpendicular to that velocity vector. In light of what we talked about previously, where we think about a perpendicular, so this would be a perpendicular, there is no a parallel component, right? So a parallel throughout the entire circular path is always 0. So I'm going to just put that little note here. A parallel is always 0 if we're going in uniform circular motion. If there was an a parallel, right, if I had a component here that's going in this direction, that would mean that my speed is changing. So I have to know if we're doing constant speed around that circular path, then that means that my a parallel has to be 0. All of the acceleration is directed perpendicular to that velocity vector. So all of that acceleration, if we look, these are all actually directed toward the center of the circle. So if I extend each of these to a certain point, they would all extend to that center of the circle. So we frequently will call or refer to the acceleration, this perpendicular acceleration, as a radial acceleration. So that a perpendicular is equal to, we call this an a rad. Sometimes you'll just see this as an a sub r. So I'm going to write all of the variations here. These are all the same thing. So a rad, this is equal to a sub r. And we do have a little equation. We'll talk a little bit later about how this connects to or where we get this equation. But I do want to introduce it now. So that radial acceleration is equal to v squared over r. So this is an equation that we will use a lot when we're working with circular motion, and then later when we get into forces and objects that are moving in circles, we'll come back and we'll use this equation some more. So a rad is equal to v squared over r, and that v is just the magnitude of our velocity vector, right, at any point. And r is going to be that radial distance from the axis of rotation to wherever our object is that we're interested in. This is a vector, so I'm going to also go ahead and write this in vector form. So a, for an object that's moving in uniform circular motion, has a magnitude of v squared over r, and the direction is directed, I'm going to say toward center of motion. So we can use that as our way of expressing that acceleration vector. So certain magnitude, which is the v squared over r, and it is always directed toward the center of our circle of motion. And we also have non-uniform circular motion. So if uniform circular motion was constant speed, non-uniform means we're going to have changing speed. And I pulled up this little graphic that we did in the first video. So again, just to highlight why we would have a changing speed. So if I have an object kind of moving in a circle, but I have an a perpendicular and I have an a parallel. So in this case, then we're going to have a changing speed. So I can have an object moving in a circle, but it is also going to be speeding up. So in this case, a parallel is not equal to 0. So in uniform circular motion, we only have a perpendicular. That's this little guy here, a perpendicular. And if we have non-uniform circular motion, we have both a perpendicular and a parallel. So our a perpendicular, this is still that a rad, right? So this is still that radial acceleration. And so this is still equal to that v squared over r. Again, kind of like projectile motion, when we can think about our x and y directions independently, we can think about our accelerations and how they impact velocity independently. So the perpendicular piece is going to be that a rad, and that's going to be equal to that v squared over r. A parallel is the acceleration that we've already been working with through the first part of the semester. So this, sometimes we call this a tan, so a tangent in that tangent direction, so aligned along that velocity vector. And this is just dv dt, so that's that same linear type of acceleration that we've already been working with. So if I have non-uniform circular motion, that means I'm speeding up, and we're going to connect this to our angular speed, right? So we're going to have an angular speed, which we're going to refer to as omega. So that means I'm speeding up. I'm going to be spinning faster, driving faster around a curve, and or spinning slower or driving slower around the curve, which means we're going to have a angular acceleration as well that we will connect back to our a parallel. So we'll make the connection between that linear and the angular quantity in a couple of videos.